Okay, the title of this lecture is An Introduction to Vector Space Models. We're going to introduce the concepts of vector span, subspaces, and change of basis today. This is a lot to cover in 75 minutes, but what I'm trying to do here is give big picture folks an idea of where we're going, and then we're going to move through the fall and really break down everything that goes into the big example we do today. So if the big example we do today is murky to you, that's okay. It's supposed to be that way. We're going to fill in those details as we go on. We're going to start with some smaller details that will help us just understand that big picture. And hopefully I will satisfy both learning styles, although it's certainly going to be a challenge to do that throughout this course. So let's just start with some definitions. This is a review from the primer material. And that's a linear combination. A linear combination is just a weighted sum. We have some vectors, v1 through vp. We multiply each vector by a constant and add the result. So I can here use green rectangles to show vectors. These little purple squares are constants. And so I just have a weighted sum of the vectors vi, written as the sum notation here. Alternatively, I could write this as a matrix vector product. The linear combination C would be this matrix V times A. The matrix V is composed of those columns V1 through VP, and that vector A is composed of those constants A1 through AP. I hope you recall from the primer that a matrix vector product is just a linear combination, and so here we are using that fact in reverse. I have a linear combination and I want to write it as a matrix vector product. In the primer, I highlighted it more so starting here and writing it as a linear combination. Okay, but we are going in reverse this time. We have a matrix vector product that gives us a linear combination. Geometrically, we talked a little bit about this, that if you have a positive multiple of the vector A, it would point in the same direction of A. A negative multiple of A points in the opposite direction. And when we add two vectors, it's like we walk in the direction and length of the first, and then the direction and length of the second. It's also said that we place the tail of the second vector to the head of the first. So to illustrate, let's take an example. A plus 2b. The vector A is as shown. 2b would be the vector that is 2 times the length of b, pointing in the same direction. And so when we place that 2b, the tail of it, to the head of A, we walk in the direction of A, and then we walk in the direction of 2b. The resultant vector is where we end up, A plus 2b. We also talked in the primer about linear dependence. And for the algebraic definition of linear dependence, we have that a group of vectors, v1 through vn, are linearly dependent if we can find some corresponding scalars, alpha 1 through alpha n, that are not all 0, such that the linear combination formed by those scalars and those vectors is equal to 0. Of course, this on the right-hand side is the 0 vector, the vector of all zeros. It's not just the constant 0, because I'm adding vectors. Now, when things are linearly dependent, that means that at least one of those vectors is a perfect linear combination of the others. So, for example, if I have that 2v1 minus 2v2 plus for v3 is equal to 0, again, the 0 vector, well, then I could solve for v1 here and show that v1 has a perfect linear relationship with v2 and v3. So that's what we call perfect multicollinearity when we are in the field of statistics, or linear dependence in more general field of math. Now, there's nothing special about v1 here. I could have easily solved this equation for v2 or v3. I'm just showing that there is a perfect relationship between these columns. On the other hand, the vectors v1 through vn will be linearly independent if the only way that this equation has a solution is when all the alphas are equal to 0. Obviously, if I multiply everything by 0 and add it together, I'll get 0. So that's what's called the trivial solution. So if you can only have the trivial solution, then you are linearly independent. But now let's talk about linear dependence geometrically, which is something we haven't quite done yet. Two vectors are linearly dependent if they're multiples of each other. So if they point in the same or the exact opposite direction. An example in real data of two vectors that are linearly dependent would be time measured in minutes and time measured in seconds. Obviously, there are 60 seconds in every minute, so if I multiply time in minutes by 60, I would get the time in seconds. Now, more than two vectors are linearly dependent if at least one is a linear combination of the others. So if you want a real-world example here, if I had a perimeter, length, and width of rectangular gardens, I would find that perimeter is equal to 2 times length plus 2 times width. But when we're just looking at vectors on a plane, this concept of linear dependence is a little fun to explore. So let's look at these two vectors I have, A and B, and the question is, can I add a third vector that's linearly independent of A and B? And we'll just explore this question by throwing some random vector on there. Can I reach the tip of that black arrow with a linear combination of A and B? Now you have to recall, a linear combination means I can only walk in the direction of A or the opposite direction, in the direction of B or the opposite direction. And what you'll find is, yeah, I can reach that point. If I walk maybe 2.1 times A and then negative 2, I don't know, maybe it's more like 1.7 times B, I can reach that black arrow. So that doesn't count. That is not linearly independent because it's a linear combination of A and B. Let's try another one. Let's try this little arrow down here. Can I reach that vector? Only walking in those directions. Now you can pause it and think about it yourself for a little while. As I reveal the solution now, if I walk in a negative direction of A and a positive direction of B, I will get there. So it turns out that the answer to this question is no, I cannot add a third vector that's linearly independent of A and B. And to formalize this, we will introduce the notion of vector span. The span of a single vector, V, is the set of all scalar multiples of V. So in set notation, I would write the span of V is alpha times V for all constants alpha. So any vector that can be written as a multiple of V is in the span of V. The span of a collection of vectors, V1 through Vp, is the set of all linear combinations of these vectors. So any vector that can be written as a linear combination of V1 through Vp is in the span of the set of those vectors. Let's look at an example. We'll start with just one vector, A. The span of A is the set of all scalar multiples of A. So any vector on this dotted line is in the span of A. Now, what happens if I want to know about the span of A and B? I have two vectors in my set here. Well, it's the set of all linear combinations of A and B. So let's start exploring that. I can put a number times A plus 0 times B. Well, that would just give me all scalar multiples of A, right? Any number I put in here in this box, as long as I have a 0 times B, will give me, again, anything on that red dotted line. I can do the same thing for B. If I put a 0 times A plus anything times B, I will get something along the blue dotted line. Okay, and now when I think about putting those two concepts together and allowing some multiple of A plus some multiple of B, well, I can start with just 1 times A plus any multiple of B would allow me to be anywhere on this blue line here. If I had 2 times A plus any multiple of B, I would be allowed to be anywhere on this blue line. If I had negative A plus any multiple of B, I would be allowed anywhere on the bottom blue line. And I hope you can see that I certainly don't need to stick to integer multiples of A, right? I could have 0.5 times A, 0.25 times A, and soon I see that I can reach any point in the plane with a linear combination of A and B. So therefore, the span of A and B is R2. Now, you'll recall again from the primer material, I used R with a superscript number to denote the dimension of the space. So this is a two-dimensional plane, two space. Now, let's look at one more example. What's the span of two linearly independent vectors in R3? Well, if you kind of think about yourself in space and you think about yourself holding up two pens that are not pointing in the same direction, you are kind of looking at the same exact situation we were just in, where those two pens here, maybe A and B, will form as a span a plane inside that three-dimensional world we live in. And so that plane, it's called a hyperplane, and we'll define that in a minute, is the plane that contains both vectors. That's what's called a two-dimensional subspace of R3. Now, we'll do some of these definitions here. The first, we will formally define subspace, even though it's not common for us to use this definition. If we're going to talk about subspaces, we ought to have the definition. A subspace of Rn is thought of as a flat, meaning it has no curvature, surface within that space. So it's a collection of vectors which satisfies the following conditions. First of all, the origin must be contained in the subspace. Next, if x and y are in the space, then x plus y must also be in the space. And if x is in the space, then any scalar multiple of x must also be in the space. I think what's important about a subspace is that it's an infinite subset of vectors, again, think points, from a larger space, that if you take it alone, it appears like RP, where P is less than N. So it appears it behaves just like RP. So a way to visualize this with the example we just did, I have this plane in 3 space, and if I just imagine that I pluck that plane out of 3 space, and I look at it, Well, that thing looks like R2. Not very groundbreaking here. This is not a detail that we'll really need as we go forward, but it's good to have the definitions as we use them. Now, the dimension of the subspace is the minimum number of vectors it takes to span the space. So the way I like to think about dimension is the number of axes that it would take to draw that space. Of course, maybe that's not helpful when we can't really think about drawing a 5-dimensional space or a 6-dimensional space. But that's the crux of dimension. It's the number of vectors it would take to span the space. Now, while we're here, we're going to define a hyperplane. We won't actually use this definition for this course, but we will use it later when we talk about support vector machines. So why not take the opportunity to define it since it's a linear algebra concept? A hyperplane is a subspace that has one less dimension than its ambient space. So in 3-dimensional space, a hyperplane would be a 2-dimensional plane. In 4-dimensional space, a hyperplane would be a 3-dimensional plane. Now, this is very difficult to visualize, right? It's impossible for us to accurately visualize. But it always will help to keep in mind this same picture. Whatever space we're in, just in our minds, it just will get visualized like 3 space, and a hyperplane will be visualized like a flat plane. Because as strange as it is, a hyperplane cuts the ambient space, that is the space in which it exists, into 2 parts. A part that's above it and a part that's below it. So this is odd when you get into higher dimensions and you're in a 4-dimensional space and you have a 3-dimensional subspace. It acts the same way. It cuts the space into a part above it and a part below it. So it's just like this flat divider. Very difficult to conceptualize. But now we get to do some practice. So I want you to pause the video, do these practice problems, and answer the responses in play pause it if you'd like.